All right. Hey, good morning. Today we're taking a look at quantum mechanics. So this is 4.2. Quantum mechanics. And this is our description of where the electrons are in the nucleus. Sorry, where the electrons are in an atom. They're not in the nucleus. That would be protons and neutrons in the nucleus. All right, so each electron in an atom, that's what we're working with. Again, the nucleus, once it was discovered by Rutherford, okay, a little bit later we found out there's neutrons in it as well, but not much else has changed with nucleus, at least for our sake here in chemistry 1. But the electrons, it took us a while to figure out where they were. So we knew if we just had simple orbitals, like a planetary model, the electrons would crash into the nucleus. There's nothing holding them up. And so we've come up with the model that we have today, which is quantum mechanics. And in quantum mechanics, electrons are defined, or the location of an electron in an atom is defined by a set of 4 quantum numbers. The first of those 4 is the principal. And this is the one you're probably most familiar with. We did already work with this one when we did our Kodachromium. This is the main energy level. So now I just said that we don't use the planetary model, but a lot of times we kind of use it to draw. Here's the nucleus. And then we have these rings of these energy levels that hold electrons that surround the nucleus. And the further out you get, the higher energy you're working with. And we kind of saw that when we did Kodachromium. We almost always draw 7 rings. So what do I have? 1, 2, 3, 4, 5, 6. I need one more. There's 7. And again, you just count them pretty easily. N is your principal energy level. So N equals 1 is the first one, N equals 2, N equals 3, N equals 4, 5, 6, and 7. Hopefully by the end of today, I can show you why we usually draw 7. We're not limited to 7. Theoretically, there's a lot more than 7. There's infinite, really. But for right now, we tend to just work with 7 principal energy levels. All right, so that is the first description of an atom. Now we've got a couple of different ways that we kind of recognize that and draw that out with our atoms, whichever atom we're working with. I'll continue with the notes for now, and then we're going to come back and I'll show you the different ways that we kind of recognize that. All right, number 2 is the shape, or sometimes we call this the sublevel. So the shape of the atom, the shape of the orbital that the electron is in. Now, it's not a flat planetary model. It's not like an electron just goes round and round. Instead, it's 3-dimensional. It's like a sphere. Our first shape actually is a sphere. We call it the S. There's my best attempt at drawing a 3-dimensional shape on a flat piece of paper, our S orbital. There are others. We'll get to them in just a minute. So leave some room here. The third quantum number is the orientation. Now, with a sphere, there's only one orientation you can have. Doesn't matter how you turn it. And S only has one orientation, and we represent that with a line. There's only one way you could have that S, and that's the only way it can be oriented around the nucleus. So just one line that represents our one orbital for S. Got it? One more quantum number. Turning the page here, leaving some room, and that is the spin. I'm going to show that in just a second. Come back to this and leave a little blank. So no two electrons can have the same set of 4 quantum numbers in the same atom. That being said, each orbital can hold 2 electrons. The spin is that 4th number that can distinguish between the other 3. So then you can have 3 of the 4 be the same, but that fourth quantum number can't be the same, and a lot of times that 4th is the spin. So we're talking about that in just a second. Let's start off with hydrogen, and this is going to be what we call orbital notation. So watch orbital notation. A lot of people get this confused with the other one. So this is orbital notation, or sometimes we call it an orbital diagram. So hydrogen, our very first element, here he is, just 1 electron. The first energy level is the 1. The only shape in the 1 is the S. We've talked about that, and there's only one orientation of the S. So here's the energy level. Here's the shape. And here's the orientation. Just one orientation for an S. The way that we show spin, so here's kind of the weird, wacky thing. You can hold a pair of electrons in an orbital. Electrons are negatively charged. They don't want to be anywhere near each other. So the way that it works is that they spin in opposite directions. So if one spins towards you, one spins away from you. I'm not very good at doing it, but as long as they have opposite spins, they can be near each other. When we go back up here to spin, the way that we show spin is with an up arrow that represents the electron. In the direction of its spin. So the arrow represents the electron and the direction of its spin. For hydrogen, he just has 1 electron. There it is. How about helium? So helium looks a long way away from hydrogen, but really is right next to him. He's number 2. He's got 2 electrons. All right, we're going to start off the same exact way. Helium's 2 electrons are on the first energy level, an S orbital or S shape, and there's only one orientation. 1 electron spins up, and how do you think we show an opposite spin? We have an up arrow. An opposite spin is a down arrow. So up, down. And there we have helium with his 2 electrons. We've done our first orbital notations. Electron configurations, just a little bit different. Not much different though. We still start off 1s. So hydrogen has 1s. He has 1 electron in the 1s. We put that as superscript. 1s1. Helium also has electrons in the 1s, but he's got 2 of them. 1s2. It looks like 1s squared. It's not. That 2 is just telling you how many electrons are in the 1s energy level. All right, we'll take a look at the periodic table. This first row, you see the number 1 there? Why do you think it's number 1? Well, that's the first energy level. And now it's filled up. Just 2 atoms have their outside electrons in the first energy level. First energy level can only hold 2 electrons, the electron from hydrogen and 2 electrons in helium. Once we're done with the 1s, we filled that up, we move on to lithium, second energy level. So again, that 2 tells us we've filled up the 1, and now we're moving to the 2, the second energy level up. So we'll take a look at the orbital notation for lithium. 1s, again, he's got both of his electrons up, down. Then move to the 2s. Lithium has a total of 3 electrons, so there's his third electron. Electron configuration for lithium: 1s2, 2s1. So we've got his 2 electrons in the 1s and 1 electron in the 2s. All right, as you can probably imagine, beryllium then has an up arrow and a down arrow in the 2s orbital. And he has 2s2. That's beryllium. We can skip over that. But here's the thing. All right, we only had 2 atoms in the first energy level. First energy level can only hold 2 electrons. The second energy level continues. We've got more, and that's because we've got a new shape. This is known as the P shape. Little tough to draw. It looks like 2 lobes. I don't know of too many shapes in the natural world that are like this outside of electrons that we can't see. But imagine you have 2 light bulbs and you put them back to back. And then kind of those two bulb areas are these areas here. So those are the P lobes. Now, the s orbital can only have 1 orientation. That's why we drew only 1 line. But a p orbital can have 3 orientations. Go left to right. Up and down. And this one's tough to draw. Hopefully I can do it some justice. Coming out of the page at you, I make this end just a little bit bigger here. And going away into the page, away from you, make that end just a little bit smaller. So we've got 3 dimensions. We've got left and right, up and down, and then coming out of the page at you, going into the page away from you. That's our 3. And so for that reason, we have 3 p orbitals, 3 lines for 3 p orbitals. And we're going to go over rules. We've got a set of 3 rules we always have to follow, but I'm going to really get into those next chapter, or not next chapter, next section, so tomorrow. But I'm going to skip ahead to carbon and kind of introduce one of those rules. So here's carbon, 6 total electrons. I should put the C there for carbon, all right. So up arrow, down arrow on the 1s. As 1s is full, he moves on to the 2s. Up arrow, down arrow. Now that's full. Now we draw the 2p. Yes, you have to draw all 3 of those orbitals. Very important to draw all 3 of them. Later on in chemistry, those open orbitals, the ones that we don't put electrons in, are really important. So it's important to see them. They all exist again. This is the one that goes left to right, up and down, coming out of the page at you, away into the page. So there's our 3 orbitals. Now we've got 6 electrons. Here's the key. This is called the bus seat rule. If you're an electron and you're the first one onto the bus, you get to pick your seat. So you sit there. If you're the second electron onto the bus, your choices are to either sit with someone or take your own seat. You're going to take your own seat. It's the bus seat rule. You're not going to sit with someone until you absolutely have to. So carbon's second p electron, goes into an empty orbital. And this is the orbital notation for carbon. The electron configuration, 1s2, 2s2, 2p2. So there's just 6 electrons, 2 in the 1s, 2 in the 2s, 2 more in the 2p. This is what's known as p block. Ever wonder how many electrons? Just count across. 1, 2, 3, 4, 5, 6. 6 atoms means 6 electrons in p block. We saw the first 2 in carbon. Carbon, as well as silicon, germanium, everybody else in this column has 2 electrons in their p orbital. All that matters is what energy level they're on. Carbon's going to end at 2p2. There it is. Silicon will also be p2, but it's going to be 3p2. Germanium would be 4p2, 5p2 for 10, and 6p2 for lead. So that's p block. Over here where we started, and we always start a new row, we always start a new energy level with s block. That's always our first orbital. So we always have an S shape. That leaves this big area here and then this area down here. I'm going to go back to where we started. Number of sublevels equals n. Remember, we used n up here. So the number of sublevels that you can have on any particular energy level all has to do with what energy level you're on. The first energy level could only have one sublevel, the S. The second energy level could have 2 sublevels, the S and the P, the 2S and the 2P. So the third principal energy level could have 3 different sublevels. So let's take a look at someone down in the 4th sublevel. So here's potassium and calcium. We'll do potassium, number 19. So we're going to pretend like, hey, we've skipped all over the 2p. We did the 3s, the 3p, and now we're on to the 4s. So we're doing potassium. We'll do the orbital notation. Let's do the electron configuration. The electron configuration for potassium. Okay. All right. 1s2. Now, what I like to do is I like to look at this, and just like we did before, this is S block. Everybody in this first row is always going to end in S1. Which S1? Whatever number's next to them. So potassium is going to end at 4s1. All right, so I like to kind of do that. That kind of lets me know where to stop. So 1s2, 2s2, 2p6, 3s2. Again, if you're following along, if you know how to read your periodic table, you're in great shape. Here's the 1s2. It's those two. 2s is these two. 2p6 are these 6 elements here. So there's my 2p6. Then we move to the 3s2. There's our 2 3s elements. And now we do the 3p6. After we get done with argon, he'd be our 3p6. Okay, then the next element up is potassium. And he is in 4s1. That's why I told myself to stop. So there we go. There's the electron configuration for potassium. Any issues? There shouldn't be. This is correct. But what about what I just told you? There's one shape, one sublevel at the first energy level, the S. There are 2 at the second energy level, the S and the P. How many should there be at the third energy sublevel? There should be 3. but we've only got 2, and all of a sudden we're up to the 4th energy level. And that's accurate, and that's how it should be. Don't forget it. I'm pointing this out because it is kind of tricky. The third shape is really tough to draw. This is the last one I'm going to try to draw. This is called a d orbital. And it looks like a double P. So it's got 4 lobes. It's crazy. It's nuts. That is a d orbital. At least my best attempt to draw a d orbital. So the idea is that the 3D or any D is harder to make than an S. I always think of like a clown that's making balloon animals. And it's going to be a lot easier to make an S, just a perfect sphere, even if it's a little bit bigger and it requires more air. It's going to be easier to make that S than it's going to be to make this crazy, wacky D orbital. This is more energy, even though it's a little bit smaller. The 3D would be smaller than the 4S, but it's still going to be easier to make that 4S. So back to our periodic table. We go to 4S. K, Ca, potassium and calcium are 4S. Right here on scandium. Do yourself a favor and write 3D. After the 4S, we go back to the 3rd energy level, and now we have our d orbitals. All right, well, let's say you're asked how many electrons a d orbital can hold. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Just count on the periodic table. This middle block here is what's called D block. It can hold 10 electrons. Again, if you're playing along and if you're recognizing patterns, back to our orbitals over here, that means there are 5 different orbitals for the D. Again, recognize these patterns. 1, 3, 5. Why do I know that there's 5? 10 elements, that means 10 electrons. Divide that by 2. 2 electrons per orbital. Think about the arrows. Up arrow, up arrow, up arrow, up arrow, up arrow. Down arrow, down arrow, down arrow, down arrow, down arrow. That would be a total of 10 electrons. 2 arrows per line. If I need to get 10 arrows in there, it's going to take 5 lines to do it. So that's D block. And like I said, it starts after the 4 has already been opened. Here's 4S1, 4S2, back to 3D. It's just kind of a weird thing you have to remember, because again, it's a higher energy level. Even though 4 is bigger, it takes more energy to make this orbital. The orbital notation for vanadium. Here's vanadium, number 23. And follow that bus seat rule. Up, up, up. Down, down, down. Up, up, up. Down, down, down. And then finally, we come back to the 3D. There should be 5 orientations for that, 5 different ways you can write a D. Now we only need 1, 2, 3 electrons. Vanadium only goes 3 into D block. There's the 3 electrons for 3D, and that is our orbital notation for vanadium. Hopefully you're starting to follow along with the periodic table here, starting to catch some of these things. The more practice you do, the better at it you're going to get. After 3D, so that'd be the end of 3D would be zinc, we go into 4P. So there's 4P with its 6 atoms or 6 electrons. Come back and we start 5S. I'm going to skip ahead to 6S. So here's my 2 6S elements. Something you need to notice. Hopefully you already have, and if not, I'm pointing it out right now. Number 56, barium is not followed by number 71, lutetium. We should all be able to count. 56 does not go to 71. I don't know if you've been in my room recently, but take a look at the periodic table on the board up front. This block here technically fits in right there. And again, count those numbers, 56, 57. Same thing with radium down here, it goes 88, 89. So watch, every time you're working with elements down here, they come to what is down here. This is called the F block. So our next orbital, I'm not even going to try to draw this one. Our next orbital is the F, and it's like a double D. It's got 8 total lobes. Again, like I said, I'm not going to try to draw it. Following along with our patterns down here. And again, if you forget the patterns on the test, count the elements. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. There's 14 elements. That means 14 electrons. 2 electrons per orbital, 14 divided by 2. Means an F has 7 different orientations. You won't draw this very often. I don't give you too many really big elements. But the F has 7 different orientations around the nucleus. Pretty nuts. It's pretty gigantic.
Daniel Bond, please come to the front office.
So this is our F block. Again, think about it. The number of sublevels equals N. So where would we first open up F? On the 4th energy level. 3rd energy level can have 3 sublevels. The 4th energy level can have 4. So the first time we see an F is on the 4th energy level. So right here, I'm going to write 4F. Do yourself a favor and do the same thing. This is our F block. And again, I know it's crazy, but we follow 6S by going all the way back to 4F. 6S goes all the way back to 4F. It's just really hard to make one of these guys. Actually, it'd be easier to make a 6S than to make a 4F, because again, it's a big, gigantic. I'm not going to try to draw it. It's going to have 8 total lobes. After 4F, you come back up. 71 follows 70. And this is back to D block. Which D? Well, 3D, 4D, 5D. So D is always 1 behind. F is always 2 behind. 6th energy level goes back to 4F. 4th energy level goes back to 3D. So 1 behind, 2 behind. So 5D all the way across. All right, now we get to P block. P block is back to being on the correct level. So that's 6. 6P is here. 7S. So now we're at the 7th energy level, followed by, we come down here. This is 5F. Back up to 6D. And finally, 7P. And that's why, at least as for right now, we've only got 7 energy levels, 7 rings around the nucleus. All of our atoms, all the electrons we have for those atoms, all 118 electrons, can fit onto these 7 rings, these 7 energy levels. So that's why we only go up to 7. As far as shapes go, as for right now, we only go up to the F. So you need to know the S, the P, the D, and the F. Eventually, someday, theoretically, it already does, go past the F, but for right now, we only work out to the F. We can fit all the electrons we have in the F. But eventually, we'll go beyond the F. And that'll be pretty crazy. You guys get to see an F in your homework tonight. Again, I can't draw it, but I have a diagram, a question with one on your homework tonight. So take a look. Guys, the next couple of days, we add just a little bit to this stuff. So practice, get better with it. I think you will if you are practicing, and we'll take a look at the answer keys as we go. And soon, then, soon this will start to make more and more sense. Work with it, you'll get there. Every year is the same, and people get there every year. So I'll see you tomorrow when we go over the 3 rules. Adios.